Hello, calculus students. So sorry I didn't get a chance to mention this in class. Taking off, well, I'm not taking off the week. I'm just not physically present in Radford for the week. So we're going to have to do this by YouTube video. Class continues. We're not slowing down the pace at all. We are continuing at our regular pace. We just have to do this by the videos, and then if you have questions, email me, and then also come into class the following Tuesday, because I'll have these lectures for this Tuesday and this Thursday. So the following Tuesday, which I think is the October 7th, come in with questions on this material, and we'll go from there. These lectures, videos are going to be much shorter than in class. Because in class, of course, we spend a lot of time, I spend a lot of time giving you a problem and giving you time to work it out, and we'll discuss them. Obviously, I won't do that here, so what you need to do is when I give you a problem, pause the video and then restart it after you've solved the problem. So this will be, I'll do an entire lecture's worth right now. So to start off with, we have gotten up to section 9.6, 9.7, and 9.8. 9.8 was higher order derivatives, which just means like second and third derivatives, which we've already been doing. I don't know why that's a separate section. It's just you can take the derivative of a derivative and so forth. And then 9.6 was the chain rule. So in 9.7, which actually we kind of skip, but there's a great table, table 9.5, which is a summary of derivative formulas. Basically, the most important thing that you need to be mastering right now are the product and quotient rules, which we've already done, and then the chain rule. The chain rule says this. If you have some function, let's say you have like f of x is, say, some function of u of x, and say the whole thing is raised to the power of 3. The way we would do this before is if it had been just f of x is equal to 3x cubed, then you know the power rule. Well, let's do plus 2x. The power rule would just tell you that the first derivative of that is this comes down here, and this becomes 9x squared, and then the slope of 2x is just 2. So done. And then if you want to take the second derivative, now this comes down, and this becomes 18x. The 2 disappears. That's it. The third derivative of 18x is 18. The fourth derivative is the slope of a horizontal line is 0. And then the fifth and every other derivative is 0 because it just, the slope of 0 is 0. The chain rule tells us that if there's some function and we're doing another function to it, in this case we're taking u and we're cubing it, then what we have to do is first we're going to treat this as if we're just going to take the derivative of this piece right here, which would be 3 times whatever's in here times, or to the power of, and then reduce this exponent by 1. But the chain rule tells us we're not done, because now we have to take the derivative of what's inside of here and multiply it. So an example would be, so let's say that f of x is equal to this down here, say 3x squared plus 2x, and then the whole thing raised to the power of 3. The way to find the derivative of that is we use the power rule, so it'd be 3 times that squared, so 3x squared plus 2x is inside there. But we have to multiply it now by the derivative of what's inside of here, and that would be 6x plus 2. Oh, down here I had a cubed. Whatever. That's fine. So that's why it's called the chain rule, because basically we're taking derivatives, the main derivative and the derivative of what's inside, and then in principle there could be other derivatives too, if you had a function of a function of a function. So with that said, you should have already been doing the homework on the chain rule and gotten good at that. This table has lots of good examples. So let's do, for example, this one down at the bottom, which says y is equal to x minus 1 over x squared plus 3, the whole thing cubed. How do you do that? Well, we take the power rule, which says 3 times that mess squared, because we reduced the exponent by 1. But now we have to multiply that by the derivative of what's inside of here. So the derivative of what's inside of there, now we have to use the quotient rule. So we use the power rule to go from here to here. Now we use the quotient rule to find the derivative of this. So the quotient rule, if you'll remember, and I always forget it. I always forget which order it goes in. It's on page, in my book, 593, and it's v du minus u dv. So if you have u over v, the derivative of that is v du minus u dv over v squared. So applying that here, why don't we just figure out, because we need to multiply this by something. So let's figure out what the derivative of this is using the quotient rule. So here's our u and here's our v. So in other words, we're going to do v, which is the bottom, x squared plus 3, times the derivative of the top. Well, the derivative of the top is 1 minus 0. So 1, so that nothing happens there. Minus u, in the case this is the numerator, so x minus 1, times the derivative of the denominator, which is 2x, and that thing over the denominator squared, which is x squared plus 3 squared. Now let's simplify that. So, so this becomes x squared plus 3 minus, and then this factors into here. We get 2x squared minus 2x over, and then when you FOIL this, you're going to get x to the 4th plus 6x squared plus 9. Or actually, yeah, that's correct, but I'm realizing what's going to happen. So I'm actually not going to FOIL that at all. I'm just going to keep it as x squared plus 3 squared. And then now I'm going to simplify the top. So this is x squared plus 3 minus 2x squared plus 2x. So the minus gets distributed in there. So this gives me minus x squared plus 2x plus 3 over x squared plus 3 squared. Now what we've done, this is the derivative of what was inside of here. So in other words, this whole thing is what's going to be multiplied here. So this becomes minus x squared plus 2x plus 3 over x squared plus 3 quantity squared. So we've got the derivative. That is the answer, but I think that we can simplify this a little bit more. And how exactly can we simplify this? Well, what I'm going to do is I'm going to expand out Actually, what do they have as the answer? And let's see how they... Oh, they don't even... Oh, excellent. They don't give us an answer. What? Okay, well, okay, so we'll just do it. So, so this becomes 3 times x minus 1 squared over x squared plus 3 squared. What I did was I factored in the squared into the top and bottom, times minus x squared plus 2x plus 3 over x squared plus 3 squared. And the reason I did it this way is now I can see the denominators are the same, so I'm going to multiply those together. And so this becomes 3 times x minus 1 squared times minus x squared plus 2x plus 3 over x squared plus 3 to the 4th. And then you can simplify this further by foiling this and then multiplying it by this. Anyway, this is a mess. But this is the first derivative of this. And the key, the take home from this is in order to get the derivative of this, I had to do 3 things. I first had to do the power rule. Then the chain rule told me I had to take the derivative of the inside. But to do that, I needed the quotient rule. So this is a really good combination of everything you've learned so far. So this table on 9.5 gives you lots of examples of when to use the power rule, when to use the product rule, quotient rule, chain rule, and all this stuff mixed together. So the new material... and this is old material, but this is a review. The new material is, for whatever, I don't know why in this book they go from derivatives, I mean, just kind of the mathematical derivatives, then to applications, which is the stuff that really matters to you all in business, and then later in chapter 11... we go back to more derivatives. In chapter 11 is derivatives of logarithmic functions and exponential functions. So I think the better idea would be let's get done with all of the mathematics of the derivatives first, and then we can go back to 9.9 and do applications, and then it turns out all of chapter 10 are applications. Optimization in business, minima and maxima, and I can explain to you why those matter to you. The point is, chapter 10 and section 9.9 are all about applications, so I would rather postpone that until the next lecture, and instead right now just finish up with derivatives. So once again, the most important things for you right now are the product and quotient rules, the chain rule, and of course the power rule, which I just discussed, but I think most of you are getting comfortable with the power rule. So those 3 things are really key. In fact, if you remember, we derived the power rule in class, or I did, and showed it to you, and I know it was kind of complex for some of you, but the point is, you should know what the power rule is by now. We've done that a lot. Product and quotient rules, and then the chain rule. Those are your 3 really powerful rules for now. So, chapter 11 is going to be derivatives of 2 things. 1, logarithms, and 2, exponents. And here's what they look like. First of all, what the heck is a logarithm? It is explained right here on page, it's in my book 702, but it's 11.1. A logarithm is the opposite of an exponential. And we've already done this in class, but review never hurts. So if you want to know, like, for example, if you know that x squared equals 7, and you want to find x by itself, then what you do to undo that square is you take the square root, and you get x is equal to plus or minus the square root of 7. And if you had x to the 5th equals 7, then to undo that, you take the 5th root of 7. And by the way, there's no plus or minus in this case, because whenever the exponent is even, then your solution will have negative solutions. But when your exponent is odd, there's only one solution. But what if instead of x to the 2 equals 7, you had 2 to the x equals 7? In other words, you're asking, what number do you raise 2 to in order to get 7? Well, try some numbers. How about 2 to the 1? Well, that's 2. 2 to the 2, that's 4. 2 to the 3 is 8, which means that x is going to be some number between 2 and 3. But how do you actually find it? Without logarithms, there is no way to find it. Logarithms are the inverse function, or the inverse activity of exponents. So the way you would do this, the way you would write it, is log base 2 of 7, and that's what gives you x. These two things are the same. They're the same equation. It's just that, just as these two are the same equation, it's just that this doesn't tell you what x is, but this does tell you what x is. Same here. This doesn't tell you what x is, but this does. Now, the way to put that in your calculator, unfortunately, your calculators do not have this function. And you might object and say, well, hold on, there's a log button on my calculator. Well, on your calculator, that log button is assumed to be base 10. So you're going to have two buttons on your calculator. One will say log, and there's another one that will say ln. This one is assumed to be base 10, and this one means log base e. So right now, with the skills that you have, there's no way for you to find this. What I can tell you, and the only reason I'm telling you this is because I don't want you staring at this and saying, I don't know how to do this. The way you do this is there's a rule of logarithms which says that log base a of b is equal to the log base anything, it doesn't matter, we'll call it log base n of b over log base n of a. And the beauty of this is that n can be anything, including, it could be 10, or it could be e. And the good news is, on your calculator, you have both log base 10 and log base e. So if I want to figure out what log base 2 of 7 is, then what I can do is break it down into log base 10 of 7 divided by log base 10 of 2, which on your calculator you would simply write as log 7 divided by log 2. And that would give you the answer. So do that right now. Once you get that number, and by the way, another thing you could also do is it's the same thing as natural log of 7 divided by natural log of 2. These two will give you the same answer. Once you get that number, go and confirm that it satisfies this equation. So get this number, which is going to be 2 point something, and then put in your calculator 2 to the power of whatever number you got there, and see if you get something that's close to or equal to 7, and you should. So in other words, a logarithm is the undoing of the of an exponent, of an exponential growth. So on page, all right, this 11.1, here is what y equals natural log of x looks like. And if you have a graphing calculator, you can confirm that. This is what it looks like. So, for example, if the function f of x is equal to natural log of x, what is f of e? Remember, e is a number. It's 2.71 something. It's a number. Well, here's how you do it. F of e is equal to the natural log of e. But remember, natural log means log base e of e. So what this asks is, what number do you have to raise e to in order to get e? This is the question. What is x under these circumstances? E to what power equals e? Well, obviously 1, right? Which means the natural log of e better be 1. Well, let's look at the graph here. Remember, e is 2.7 something, so let's look. Right at 2.7 is about right here, and go up to the curve, and you will see that that corresponds to a y value of 1. And that makes sense. What about the natural log of, let's try natural log of 1. What is that? So what that asks is, what do you have to raise e to in order to get 1? Well, any number to the power of 0 gives you 1. So in this case, x is 0. So if you put in 1 in the graph, you better get 0. Let's see. Right here, if you move over to x equals 1, you see that we're right on the x-axis. We're right at y equals 0, so good. Last question for you. What is the natural log of 0? The question is, what do you raise e to in order to get 0? Well, just start putting in some numbers. Put in any numbers you want here. What you'll find is that e to the minus, let's say if you said e to the minus 2, that's the same as 1 over e squared. That's going to be, I don't have my calculator with me. In fact, I'm filming with my phone, which is my calculator. Sorry about this, I'm having technical difficulties. 1 over e squared is going to be, I don't know, like 0.12 or something like that. But that's not 0, okay? So what about e to the minus 20? Well, that's 1 over e to the 20th, which is going to be a really small number, but it's still not going to be quite 0. It's going to be a little bit more than 0. And it turns out no matter how negative you make this number, you will always be greater than 0. In other words, there is no number that when you raise it, raise e to the power of it, you get 0. And that's why in this graph, when x equals 0, there is no value, because this curve asymptotically approaches this axis. There is no such thing as natural log of 0, or log base 10 of 0, or log base anything of 0. You also can't get a negative number either, because you can't raise e to the power of a number and get a negative value. That's impossible. So that's why this graph looks as it does. So that's log and natural log. Log and natural log are going to look very similar. It's just that they're going to be adjusted in height is the only difference between the two. So then we want to know, of course this is calculus now, so we want to know, well, what is the derivative of a function, a logarithmic function? And it just turns out it's actually super easy. The derivative of natural log of x is just 1 over x. It's beautiful. In fact, there's a nice little explanation and drawing on the next page explaining why it happens to be 1 over x. And so then using the chain rule, and there's the derivative right there. And remember, by the way, that e was a very special value, because e to the x, if you take the derivative of that, that gives you e to the x. So that's why the natural log of x, its derivative is just something nice and simple, 1 over x. So anyway, but using the chain rule, let's say it wasn't, we don't want to take the derivative of natural log of x, we want to take the derivative of something a little bit different than that. We use the chain rule. So here is an example. Example 2a, which says f of x is equal to the natural log of x to the 4th minus 3x plus 7. And we want the derivative of that. Well, all we do is, the first thing we do is we ignore what's inside of here and we take the derivative of natural log, which is 1 over what's inside here. So the first thing we do is 1 over this. But now we have to use the chain rule and find the derivative of this and multiply it. So the derivative of this, using the power rule, is 4x cubed minus 3. So I'm just going to move this to the numerator, and this is equal to 4x cubed minus 3 over x to the 4th minus 3x plus 7. And that is explained in the solution right on the next page. And there are a few other examples too. Like here's an example that's going to require the product rule and the chain rule, and so forth. So review these so that you get comfortable with taking the derivative of natural log. We're at about 28 minutes now, and I didn't want to make these lectures longer than 30 minutes because it's very dense material. Also, it's going to take forever to upload on YouTube. So I'm going to cut this off right now. But what I will say before I do that is I want to offer extra credit to students for doing their homework and actually doing this class. So what I want you to do is to email me as soon as you get this. Here's my email address. And I simply want you to write in it, in the text of the email, your name, as well as something you understand in this class and something you don't understand in this class. That's it. Your name, something you understand, something you don't understand. The first one to send it to me gets 5 bonus points on the next test. So that's half a grade, half a letter grade. That's a lot. And then everyone else who gets it to me before Tuesday's or before Thursday's class will get an additional 2 bonus points on the next test. So that's all you got to do. Email me and you get some extra credit. And that will help me to determine who is watching these and who is not. And then in the next lecture, I'm going to move on to exponential functions for about 10 minutes. And then after that, we'll move on to applications. So your homework for this section, 11.1, has been posted on D2L. So your homework until next class will be your homework for 11.1. And up until now, you should also have finished all homework up to section 9.8. So we're going from 9.8, skipping to 11.1. Next class we'll do 11.2, and then go back to 9.9.